Hello, I'm Dr. Alla Kammerdiner. Welcome to Discrete-event simulation. This is Lecture 4, Fundamental Simulation Concepts. I will talk about components of a simulation model and event-driven hand simulation. Let's take a look at a simple processing system. Here we have some blank parts arriving in the queue, and it's a first in, first out queue. So you can see here parts 7, 6, and 5 already in the queue, and part 4 is being processed by a machine. So part 4 is in service, and after it's finished being processed, it will depart from the system. So the general intent here is to estimate expected production, and we also want to know often the waiting time in the queue length, proportion of time machine is busy. It's very important to pay attention to time units when simulating a simple processing system. We can actually use different time units in different places, but we need to make sure to declare them and also to be careful to check units when specifying inputs. It is also important to declare base time units for internal calculations and outputs and be reasonable in terms of interpretation and round of errors. Let's take a look now at model specifics for our model. So initially at time 0, we have our system empty and idle. Base time units are in minutes, and input data are assumed to be given for now, and they're in minutes. So here's our input data. We have part number, its arrival time, its inter-arrival time, and the service time. So for part 1, you can see the arrival is at 0, inter-arrival time is 1.73, and the service time 2.9. Here's a second part, and this is information in this second row. There is information on arrival, inter-arrival, and service times for part 2. And the next is part 3, part 4, part 5, 6, 7, 8, part 9, part 10, part 11. So we stop when 20 minutes of simulated time have passed. So the goal of our study is to better understand output performance measures. So here in our study, the output performance measures are total production of parts overrun, denoted by P. Then we also have an average waiting time of parts in the queue, and it is computed using this formula, where capital N is the number of parts completing the queue waiting, and variables WQI are waiting times in queue of I's part. So we also want to know the maximum waiting time of parts in the queue, and this is how it's computed. It's just the maximum among the WQIs. So we also want to know time average number of parts in the queue, and this is how that's computed. Because our run is until the time 20 minutes, then it's gonna be the time averaged by 20 minutes, and we have QT representing the number of parts in the queue at time t, so we're integrating the QT from 0 to 20 minutes and then divided by 20 minutes. And the maximum number of parts in queue is another output performance measure, and this is how it is computed. So here it's just a maximum from 0 time to time 20 minutes of QT. We also want to know average and maximum total time in the system of parts. This is also known as cycle time. So the total time in the system is known as cycle time. And this is how the cycle time can be computed depending whether we're looking at the average or maximum, we're going to have two different formulas. So the first one there, where we sum up the times in the system for ith part, and then divided by the number of parts, that's the average. And the next one, it's the maximum cycle time. We also want to know utilization of a machine. That's an important output performance measure. And utilization of a machine means the proportion of the time that the machine is busy. And this is how it can be calculated. So first we look at BT, which is either 1 or 0 at each time, depending on whether the machine is busy at that time or if it's idle. And then we integrate the BT over time from time 0 minutes to time 20 minutes and divide it by 20 minutes. There are, of course, many other possible output performance measures, but we're not going to take a look at those. For now, we're just focusing on the ones that we discussed. So now let's take a look at the analysis options. Of course, we could do some educated guessing. So the average interarrival time is about 4.8 minutes, and the average service time is 3.46 minutes. So on average, parts are processed faster than they arrive. System has a chance of operating in a stable way in the long run, right? It might not explode because we have this property that on average parts are processed faster than they arrive. But it's also important to notice that it's set on average, right? So sometimes the parts might arrive faster than it's already finished, the other parts that haven't been yet finished processing. If all interarrivals and service times were exactly at their mean, there would never be a queue. But data clearly exhibit variability, so we might have a queue. If we had an average interarrival less than average service time and this persisted, then the queue would explode because we would keep getting more and more parts and not getting them out of the system. So of course the truth is between these extremes, and guessing has its limits. So another analysis option is to apply queuing theory, and it requires additional assumptions about model. The popular and simple model is MM1Q. Interarrival times in this model are exponential, and service times are also exponential and independent of interarrivals. In this situation, we must have the expected service time less than expected interarrival time. And in that case, we would have steady state, long run, forever analysis that we could do. So the exact analytic results, for example, average waiting time in a queue is the square of service time of average service time divided by the difference between the average interarrival time and average service time. Of course, there's a problem with this model because it's very simple, and so the questions of validity comes up because it might not be applicable to all different situations. Another question is estimating means and also a time frame in terms of simulation, because this is more appropriate for a steady state in the long run. If we're looking at a short time period, we can really apply these results. But it's still often very useful as a first cut approximation. So let's take a look at components of simulation model. Of course, one of the most important components is entities. These are players that move around, change status, affect, and are affected by other entities. They're dynamic objects. They get created, they move around, and leave, possibly. and they usually represent real things. In our model, entities are parts. We could possibly have fake entities for modeling some tricks. Example, breakdown demon, break angel, and so on. The Arena has built-in ways to model these examples directly. Usually, we have multiple realizations of an entity floating around. And we can have different types of entities concurrently. Usually, identifying types of entities is first thing to do in building the model. Another important component of simulation model is attribute. So attributes are basically a characteristic of entity, of all entities, and these attributes, they describe the entity and they also differentiate between different entities. All entities have same attribute slots, but they have different values for different entities. Example, we might have parts, right? The single type of entity, but for different realization of parts, right? Part 1, part 2, we had different time of arrival. We could have different due date, we could have different priority, we might have different color. So just for example, attribute value is tied to a specific entity, and it's local to entities. It's local variables for the entities. Some attributes are automatic in Arena, but some we must define. So another component is global variables. So it's very important not to confuse these local characteristics of entities that we just discussed in terms of attributes with variables. So variables are not attributes. They're global variables. They reflect a characteristic of a whole model, not of specific entities. And they are used for many different kinds of things. For example, travel time between all station pairs, number of parts in the system, or very often a simulation clock, and that's a built-in Arena variable. Name, value of which there is only one copy for a whole model. So for the whole model there is only one copy of each variable, but we might have multiple attributes and they correspond to the entities, right? Realizations of different entities. So variables not tied to entities, unlike attributes. Entities can access and change variables. They are rewritable, some built in by Arena, and you can define others. So another very important component of any simulation model is a resource. So resources are what entities compete for. Example, people, equipment, space. Entity seizes a resource, uses it, and then releases it. Think of resource being assigned to an entity, not an entity belonging to a resource. A resource can have several units of capacity. Example, seats at a table in a restaurant. Identical ticketing agents at an airline counter. It's also important to remember that the number of units of resource can be changed during simulation run. Another important component is queues. Queues are places for entities to wait when they cannot move on. For example, maybe a resource they want to seize is not available. Queues also have names, and they're often tied to corresponding resource. Queues can have a finite capacity to model limited space, and have to model what to do if an entity shows up to a queue that's already full. Usually, we need to watch length of a queue and waiting time in it. Another A key component of simulation model is statistical accumulator. So statistical accumulators are variables that watch what's happening. They depend on output performance measures desired, and they're passive in the model. They do not participate, they just watch. Many are automatic in Arena, but some you may have to set up and maintain during simulation. At the end of the simulation, they're used to compute final output performance measures, and we'll look at this and how to use the statistical accumulators later. So statistical accumulators for simple processing system, number of parts produced so far, total waiting time spent in the queue so far, number of parts that have gone through queue, maximum time in queue we've seen so far, total of times spent in system, maximum time in system we've seen so far, and area so far under queue length of curve QT, maximum of QT so far, area so far under server busy curve BT. Now let's take a look at simulation dynamics and focus on event-centered simulation dynamics. We need to identify characteristic events and decide on a logic for each type of event to affect state changes for each event type. Observe statistics, update times of future events, maybe of this type or other types, keep a simulation clock and future event calendar. Jump from one event to the next, process, observe statistics, update event calendar. We must specify an appropriate stopping rule, and usually it's done with general purpose programming language, C++, Java, MATLAB, Fortran, etc. Events for simple processing systems. First of all, arrival of a new part to a system. During arrival, we need to update time persistent statistical accumulators from the last event to now, such as area under QT, maximum of QT, right, which is our length of the queue, and then area under BT, which is our utilization. We also need to, during arrival, to mark arriving part with the current time. If machine is idle, we're going to start processing, we schedule the departure, make machine busy, and tell a waiting time in queue. If the machine is not idle, in other words busy, we need to put part at the end of a queue, if it's first in, first out queue, which in our case it is, and an increase queue length variable, and also schedule next arrival event. Another important event for our example is departure. Departure is when service is completed. So at that time, we need to increment number produced statistical accumulator. We need to compute and tally time in the system, or cycle time. And we need to update time persistent statistics, just as an arrival event. And if queue is not empty, then we take the first part out of the queue, we compute and tally its waiting time in the queue, and begin service or schedule departure event. Otherwise, if it's empty, if the queue is empty, we make machine idle. Important to know that there will be no departure event scheduled in the future events calendar, which is as desired. And at the end, right, which is another important event, we need to update time persistent statistics to end the simulation, compute final output performance measures using current or final values of statistical accumulators, and after each event, event calendar stop record is removed to see what time it is, what to do. We also must initialize everything. So when we look at the simulation clock variable, which is internal in Arena, we also need to use event calendar, which is list of event records. And it includes entity number, event type, time, and event type. We need to keep ranked these events in increasing order on event time. And the next event always in top record. Initially, schedule first arrival and the end, or departure. State variables are important. They describe current status. For example, service status. BT is 1 for busy or 0 for idle. Number of customer in queue, QT. Times of arrival of each customer now in queue. A list of random length. So let's take a look at simulation by hand. We manually track state variables and statistical accumulators. We use given interval and service times, and we're gonna keep track of event calendar. We're gonna lurch clock from one event to the next, and we will omit times in the system, maximum computations here. So you can see more details in the Arena textbook. So let's go ahead and get started. So when we start, the system is idle, and at time 0, the clock shows now. We have BT, which is the utilization of the machine. The machine is idle, so we have 0, and then there's no parts in the queue, so QT is 0. And notice we have this event calendar, right? And the event says that part 1 arrives at 0. And it also has another event which tells us when the simulation ends, and it ends at 20 minutes. We have number of completed waiting times in the queue, which is still 0. Total of waiting times in the queue is 0. And of course the rest, such as area under QT and BT, are also zeros. And here we're gonna start plotting our QT and BT graphs, right? Which is the number of queue and the busy or idle, right? The utilization of the resource. These are our inter-arrival times for different parts, and below them are the service parts of when how long it takes for the part to be processed. So the first one is inter-arrival time for part 1, and this first one is a service time for part 1, right? The next one is for part 2, inter-arrival time, and this next one is a service time for inter-arrival for part 2. So let's see, at time t0, the part 1 arrives. As soon as it arrives, now it seizes the resource because it doesn't have to wait in the queue. And we have BT being changed to 1. We took care of this event, so we got rid of the inter-arrival time and the service time. It's taken into account, and we put it in the calendar. So the next event that we're gonna have is the inter-arrival, is the arrival of part 2, and part 2 arrives at 1.73, but the departure for part 1 is at 2.9. So you can see that here in the event calendar, we listed the events based on the time, right? In the matter of increasing time. We can see the number of completed waiting times in the queue is 1 because it didn't have to wait in time, so it waited just the same as waited 0. And then total of waiting times in queue is going to be 0, and so the areas for QT and BT so far are just 0, and this is the plots that we got. So next we have arrival of part 2. So we took that event of the calendar and we changed the clock, right? The clock is at 1.73 minutes when part 2 arrives. So when part 2 arrives, the part 1 is still being processed, so the machine is busy. So part 2 has to wait in the queue, and you can see that QT number is now increased to 1 because we have part 2 waiting in the queue. We have arrival times of the part in the queue, which is 1.73. And now our event calendar is updated. We still have this at part 1 at 2.9, which is a departure for part 1. But we also have soon after we have another event, which is the arrival of part 3. Arrival part 3 we get by adding the inter-arrival times, right? So here, this 1.73 is the time between arrivals of parts 1 and 2, and 1.35 is the times between arrivals of parts 2 and 3. So when we add them together, 1.73 plus 1.35, we get 3.08, which is the arrival of part 3. And this is why we have this event here. So again, number of completed waiting times in the queue is still 1 because only part 1 has completed its waiting time in its queue. And the second part is still waiting. So the total waiting times is still 0. This is the area under the QT, but the area under BT has changed because notice that we had this busy, right? We have the machine busy processing part 1 for 1.73, right? Which is all the way until the part 2 arrived, which is also a current time on our clock, simulation clock. So we got the area under BT by simply multiplying this, which is 1, right, and this, which is 1.73, right? So that gives us the area. So next, the part 1 leaves the system at 2.9, and during the departure of part 1, it also this departure of part 1, it also creates, right, the space for part 2 to be processed in the machine. So the machine becomes available, so part 2 can now see the machine. So we can see, right, the BT has changed. Well, actually, it changed back to 1, right? Because as soon as part 1 left, part 2 seized it, so it still remained at 1. But the QT changed because now we don't have any parts waiting in the system. And so you can see, right, this drop on the QT graph. And also we can add additional events to the calendar, right? So you can see at 4.66 is our scheduled departure for part 2, which is below the arrival of part 3. And so we also notice that number of complete waiting times in queue is now 2, right? Because the second part has already finished waiting in the queue, and it waited there for the time, right, between its arrival and the service time. So if we subtract, right, the service time for part 1, which was 2.9, and from that we subtract inter-arrival time, right, the time when part 2 arrived, which was 1.73, so 2.9 minus 1.73 is going to be 1.17, which is the waiting time for part 2. A waiting time for part 1 was 0, so when we add them together, we still get 1.17. And the area under the QT is 1.17, which we just get by multiplying 1 by, this time, 1.17 here of the time that passed when we had a person in the queue. So now we also have this area under the BT changed as well because we added this additional time. So altogether we have 2.9 passed multiplied by 1. So 1 by 2.9 is 2.9. So the next is when part 3 arrives. And that happens at 3.08 minutes. And so as soon as it arrives, now the QT has changed to 1. And we also can update the event calendar by adding an additional event. Notice that part 4 is going to arrive at 3.79. So now still have the same number of completed waiting times in queue because 3 is going to be waiting. So the same total waiting times, the same area under QT, but different area under BT because now we're gonna get additional time busy here for the machine. Then when part 4 arrives at 3.79, we still have the machine busy, but the number of parts in the queue has increased by 1 with the arrival of part 4. So now the QT is going to be 2, and you can see that on the graph, right? We're going to go higher up in the graph at that time. And we also updated the event calendar by adding the arrival of part 5. It's still the same number of completed waiting times in queue and the same total waiting times in queue, and we have the same actually we're gonna have additional time added, right, to get a new area under QT. So the area under QT here is basically this area here, right, plus this part here. And so we got 1.17 that we waited before, plus this additional time, which is between, right, the inter-arrival time between the two parts. So it's 0.71 here. And so when we add 1.17 and 0.71, we get 1.88. And of course, area under BT has changed, which basically is, right, this whole thing, which is 3.79 multiplied by 1, right? That gives us the area under BT. So next is the arrival of part 5 at time 4.41. So now we have 3 parts in the queue. So QT is different, it's 3. We updated event calendar by adding the arrival of part 6, which is below, right, the departure of part 2 because the time is much higher. And then we still have the same number of completed waiting times. We have the same total of waiting times, and we have some changes in terms of the QT because now, right, this inter-arrival, which was 62, we need to multiply this by 2, right, and add it to what was previously 188. So if we add to 1.88 that we had before this area under the queue of these two, we need to add this little piece here of 0.62 multiplied by 2. So 0.62 multiplied by 2 is 1.24. And so when we add 1.24 to 1.88, we get 3.12. And this is what we have here. And then that area under BT, right, is simply because we have all this, right? So all this time, which is 4.41, multiplied by 1. And so it's easy, it's just 4.41. So the next thing is the departure of part 2. As soon as the part 2 departs, right, the machine is available, so the next part seizes it, right? So now it's still gonna be BT, still gonna be 1 because we had a part that seized it as soon as the other part departed. and so we have 1, right? But the QT now decreases to 2 because 3 is being processed. Now we only have 2 parts in the queue. And so that's exactly what you see on the graph, right? This drop in the graph to the 2. And then we also added, we still have similar event calendar, except we added an additional event. Notice the departure of part 3. We calculated it, right? And because we have clock at 4.66 when the part 3 ceased the system, and we added the service time here of 3.39, then 4.66 plus 3.39 gives us 8.05. And that's our departure for part 3. And so the number of complete waiting time in the queue was 2, right? But now 3 finished its waiting in the queue, and now it's being processed. So we increase it, and now it's 3. And so we also add the time of the part 3 that part 3 spent waiting to the waiting times in the queue. And then we add add this little piece here, right, to the area under the queue, which is this little part, right, multiplied by 3. So now that we got that, we are ready for the next event, which is the departure of part 3. As soon as this part departs, right, and that's at time 8:05, there's more, right? We see the part 4 seizes the machine, and there's only 1 part waiting, so there's number of changes. You notice that number of complete waiting times is incremented to 4, and we added the waiting time spent by part 4 here, increased, and then we also increase the area under the curve, right, by this amount, right, which is basically 2 multiplied by 14.28, and then we get the event calendar updated by indicating, right, since we now know when part 4 sees the system, which is at 80.5, we can add the service time for this part, which is 4:52. And when we add 80.5 to 4.52 here, we're gonna get 12.57, which is a departure for part 4. So again, right after we updating this, the next event is the departure of part 4, and that's when 5 seizes it. So notice here, right before the queue was 1, now we change the queue to 0. BT is still 1 because it's busy, and we also can calculate the time when 5 departs. We change the number of complete waiting times in the queue, the total waiting times in the queue, the area under the curve, and the area under BT. And so the next event, as you can see, right, is the departure of part 5, which is at 17.03. And so at 17.03, the part 5 departed, so now machine is idle because there's no parts to seize it. And so we have 0 here, 0 here. We still have the same number of waiting times in the queue, the same total of waiting times in the queue, and the same area under the queue, because we don't need to add anything here, right? This area is just 0. But the area under BT has changed, right? And basically it's 1 multiplied by all this time, which is 17.03. So this is what we have right now, and we're not done yet because there is another event coming, right? The arrival of part 6. So the part 6 arrives at 18, which was 17.03. And so we also adding additional piece to the area under BT, and this is the end of our simulation. So at this time we take all of the statistics and we can use them to get our output performance measures. So using those statistics that we got, the total number of times in the queue and number of times in the queue, we can get average waiting time in the queue. So we divide 15.17 by 6, and the average waiting time in queue is 2.53 minutes per part. We also can get time average number in the queue, and that's obtained by dividing area under QT curve by the final clock value, right? Because the area under QT is the same as integrating the QT over time. So we got this 15.78, we divide by 20, this is 0.79 parts. And then we can get utilization of the drill press, we get utilization of machine as the area under BT divided by the final clock value. We got our area under BT as 18.34, and we divided by 20, and this is 0.92. And that's dimensionless because it's utilization. Typically, we have utilization, and the utilization should be between 0 and 1. So you can see this is pretty close to 1, 0.92, pretty high utilization of the machine. And when we look at the complete record of hand simulation, this table has complete record of our simulation. And what you just learned, you can use to complete Lab 2. Thank you.